All right, welcome to the second subsection of section 5.1 about orthogonal complements of subspaces. Now, this definition starts with the fact that suppose W is a subspace of RC. Maybe we haven't been talking in a lot of detail about what subspaces are in a while. That was what section 1.5 and also kind of 1.6 and 1.7 were all about. And the definition of a subspace was that it's a set of vectors in RC that is closed under vector addition and under scalar multiplication, and it also has to contain the zero vector. And we saw that that was equivalent to saying that W can be written as the span of some list of vectors. In other words, any set that is the span of some vectors satisfies the definition of a subspace, being closed under those operations, and also any subspace can also be written as the span of some vectors. So subspaces are spans, spans are subspaces. So a line that goes through the origin is a subspace. All of R2 is also a subspace. The set containing just the zero vector is a subspace. Planes through the origin are subspaces. So that's what we're talking about here. Now let's get to this definition. The orthogonal complement of W, written W perpendicular, is the set of all vectors that are perpendicular to every vector in W. So in symbols, all vectors that are perpendicular to every vector in W. And remember, perpendicular means their dot product is 0. So yeah, all vectors U in RC such that U is orthogonal to W for every vector W in the vector space W. Now let's look at an example of that here. This says A is the vector with components negative 2, 1, which is a matrix with one column. So if you just get the span of that column, the set of all linear combinations of A, that's the same thing as the column space of A as a matrix. Let's describe the orthogonal complement of the column space of A and make sure your answer agrees with this graph over here. Okay, so the definition of the orthogonal complement is that U is in the orthogonal complement of the column space if and only if U dotted with any vector in the column space of A gives you the number 0. But any vector in the column space of A can be written as some scalar k times the vector A. And let's say U has components U1, U2. We also know that Ka is the vector negative 2 times k and then 1 times k. So this dot product here, oops, I forgot the arrow. This dot product means we're going to do U1 times negative 2k plus U2 times 1k. Now at this point, we could divide both sides by k because 0 divided by k is just 0. The k's should all cancel out. You can do that as long as k is not 0. But it turns out the 0 vector, like if k is 0, then that's orthogonal to U no matter what. Like U dot the 0 vector is always the number 0. So we can just say this is equivalent to saying U1 times negative 2 plus U2 times 1 equals 0. Now, what I want to point out about this is saying In other words, that if you take negative 2, 1 as a row and do that times the vector u1, u2, you get the 0 vector, the 1 by 1 0 vector, which is just the number 0. And that's the same thing. This row, negative 2, 1, is the same thing as the vector A transpose times u in getting 0. This is the same thing as saying u is in the null space of A transpose. And you might be like, why are you going off on this tangent, Professor Smith? Well, it is because I'm trying to sort of justify theorem 5.6 before we get there. So just put this in the back of your pocket and we'll think about it later. Now, to actually find a vector in the null space, it's the same thing as solving this homogeneous equation because we have 0 over here. So we can use the same methods as before, like if we scale this by 1 over negative 2, the augmented matrix becomes 1, negative 1/2, 0, which means we can say u1 is equal to 1/2 u2, and u2 is a free variable, so it's just equal to u2. So this is equivalent to saying u is in the span of the vector 1/2, 1. In other words, u is in the orthogonal complement of the column space of A if and only if it's perpendicular to every scalar multiple of A, and you can basically just cancel out the k's in this equation, and you get this nice homogeneous equation here, which you can solve for the basic variables in terms of the free variables, and you can write any of these u vectors as a scalar multiple of 1/2, 1. So, in other words, we have the orthogonal complement of the column space of A is equal to the span of 1/2, 1, and by the way, that's also equal to the null space of A transpose. So let's make sure that agrees with the picture over here. So this blue thing is the column space of A. There's the vector 1, negative 2. And yeah, we can see that the vector 0.51 here looks perpendicular to A. And if it's perpendicular to A, it's going to be perpendicular to any other vector that's a multiple of that, right? Okay, let's look at another example here. We're going to add a dimension, go into R3 for a minute. So we're going to say B is the vector 1, 0, 3. And we're going to notice that the column space of B is the span of B for the same reason as before. Let's describe the orthogonal complement of the column space of B. And hopefully this picture down here agrees with the answer. So this is going to be the same idea as before. So U is in the column space of B's orthogonal complement if and only if U dot KB is equal to 0 for all K in R, because the set of vectors that can be written KB for all K in R is the span of B. That is the same thing as the column space. And we can again write U as the vector U1, U2, U3. So if we want to write out U dot KB, that's going to be U1 times K times 1 plus U2 times K times 0 plus U3 times K times 3. And again, you can scale everything by 1 over k, like so. And at this point, I want to notice that what we're doing here is taking 1, 0, 3 times the vector u1, u2, u3 and getting 0, or in other words, B transpose times u equals 0, or in other words, we're saying u is in the null space of B transpose. U is a vector that you can multiply by B transpose and get 0. Anyways, this augmented matrix 1, 0, 3, 0 is already row reduced, so we can write u1 equals negative 3 u3, u2 equals u2, and u3 equals u3. So all of the free variables here we just write as equal to themselves. Or in other words, the vector u can be written as u2 times 0, 1, 0 plus u3 times negative 3, 0, 1. Or in other words, we're saying u is in the span of 0, 1, 0, negative 3, 0, 1. So this is equal to the orthogonal complement of the column space of B. And we just saw that that's equivalent, like that a vector being in the column space of B's orthogonal complement is equivalent to U being in the null space of B transpose. So what does that look like in this picture? Well, yeah, the V right here is the 0, 1, 0. The U, oh, maybe this picture isn't great because I'm using U for something different. Okay, so it doesn't quite agree. Let's call that W. Okay, so this is W, and this is the V we're talking about. And anyways, yeah, the column space of B is the straight line, and we can see that both V, 0, 1, 0 is perpendicular to B. It's easy to do a dot product with this 0, 1, 0 with 1, 0, 3 and get 0. And also W, negative 3, 0, 1 is also perpendicular to B. You can check that with a dot product too. So the span of these two vectors that are each perpendicular to B gives you the orthogonal complement of the column space of B. Let's take a little break, and in the next video we will kind of see how these concepts we've been talking about work in general.